Um, I, I now begin a new chapter of my abbreviated course that I call linear algebra. This is chapter 4, which is about the determinant and the inverse. Um, so we start with the determinant. Um, it's just a number associated with a square matrix. Only a square matrix has a determinant. I not know why we're doing it, but it's going to come in handy later. If here's a square matrix, we say its determinant is this notation here, are these straight bars that look like absolute values. Remember, the determinant is a number. So this is a matrix. This is a number. You might, maybe you've already had a determinant before. I think the way it's normally taught, at least to engineers, and the way I taught it in NMath A, and in a couple of advanced engineering math textbooks, that they start out with, here's how to calculate the determinant, all the formulas to do the calculations. And then from there, derive properties. The more elegant mathematical way to do it is to start with properties. These three key properties, and we will define determinants this way. Property 1, the determinant of the identity matrix of any size is 1. That's a property that we define that way. The determinant changes signs when two rows are exchanged. Okay, that's easy enough to understand. The determinant is a linear function of any given row. That one's a little bit weird, so let's look at that a little bit deeper. Here you see this top row. It's a linear function. It's a and b plus a prime plus b prime. That means the determinant breaks up this way. Just the a, b, c, d part, and then the a prime, b prime, c, d part. Or I could do it on this lower row. Addition. Or you could break up a matrix like this, a, b, c, d. You could say it's a plus 0 and 0 plus b. And the other rows stay the same. Or if you multiply a given row, it's the same as multiplying the matrix by that constant. If you multiply a given row by a constant, say p here, then it's the determinant of the original matrix times that p. It does not mean this. It does not mean the determinant of a sum is the sum of the determinants. This takes some thinking to really understand it. You might want to come back to this chart. So now we get into derived properties. I guess I should make one more remark. Super smart people might think, oh, there might be a conflict between property 2 and property 3. Maybe if there's some linear function that, I don't know, it's sign change. Anyway, that doesn't happen. So that these three properties are consistent. They do not conflict with each other. And it's going to turn out they're going to describe almost everything. We'll get into that. If two rows are equal, the determinant is 0. Why is that true? Well, if I flip those two rows, just did a row change, it's still going to be the same matrix because they're the same row. But I change the sign when I do a row change. So the determinant of A is minus the determinant of A. The only way that can happen is if the determinant of A is 0. We'll do derive some more properties in another video. Keep these short.